So let us come back and start with additional examples. I hope once we move into the additional examples, I will try to keep you step by step. Each step I will try to show you so that you can follow it. What we will do in these examples is we use a real Smith chart. So I will show you a real Smith chart. On the real Smith chart we will see the example. You can see if you purchase a Smith chart from the market, from a bookstore, or if you download the Smith chart from the internet, the Smith chart will look something like this. It will almost exactly look like this, what I am showing here in the figure. So you will have this Smith chart like this. Once you have this Smith chart like this, then you have to use this Smith chart for solving different problems. Now let me give you one problem here. We have a transmission line which is terminated on a load ZL. We do not know what is ZL. The characteristic impedance of the transmission line is 50 ohm. The source impedance or input impedance for the transmission line is given, which is 140 plus J21 ohms. That is the input impedance. And length of the transmission line is given, L is equal to 0.1 lambda. So everything is given in terms of lambda. You need not worry about lambda. So L is equal to 0.1 lambda. Zin is equal to 140 plus J21. Z0 is equal to 50 ohm. We have to find out what is ZL, what is gamma, what is VSWR, what is YL, what is V minimum on the transmission line, what is the minimum voltage that we can see, what is the maximum voltage that you will see. So these are the things that we have to find out. Voltage standing wave ratio, reflection coefficient, the load impedance ZL, load admittance YL, V minimum, V maximum, the points of V minimum and the points of V maximum. So everything, the data is given to us. Using the Smith chart, we have to do this. Now, let us see what we have to know. To do this, look at the Smith chart carefully. You will see that there are complete circles. Each complete circle is called a constant R circle. So these red circles that you see on the transmission line, on the Smith chart, there will be many such circles. I have shown you, for example, some circles which are complete circles. These are called the constant R circles. What is meant by constant R circle is that on this circle, on each of these circles, everywhere on the perimeter of these circles, as you move along the circle, the resistance is constant. So take the first circle or the second circle or the third circle or the fourth circle. On the first circle, resistance is constant everywhere on the circle. On the second circle, resistance will be constant. It will be different from the first circle, but it will be constant everywhere on the circle. On the third circle, it will be constant everywhere on the circle. On the fourth circle, it will be constant everywhere on the circle. So as you move on these circles, the resistance remains constant. So these are called constant R circles. Small r represents that it is normalized. Capital R is the resistance. So capital R divided by Z0 is the small r. Small r is equal to capital R by Z0. So that is normalized with respect to the characteristics impedance of the guiding structure or the transmission line. So this is one part about the Smith chart. Then the next point to remember about the Smith chart is the positive arcs and the negative arcs. So there are two arcs you can see in the above part. These are written as positive imaginary arcs. So those were real arcs, these are imaginary. The circles are real because R is real, so circles are real. These arcs are imaginary. Why these arcs are imaginary? The reason is very simple. They represent the reactive part. Reactive part is imaginary, therefore on the upper part is positive imaginary arcs, lower part is negative imaginary arcs. So upper part represents XL, lower part represents XC. Now, what is the first thing to do if you are using a Smith chart? The first thing that you have to do is normalize the impedance. We are given Z in and we are given Z0. So input impedance is given, characteristics impedance is given. So we will normalize the input impedance with respect to the characteristics impedance. So Z in, small z in, which is the normalized input impedance, is small z in, capital Z in is the actual input impedance. So small z in is equal to capital Z in by Z0. That you can find out 140 minus J21 by 50. 140 by 50 is 14 by 5, 28 by 10, 2.8 minus J 0.42. So normalized impedance, first point is look to find out what is the normalized impedance. So that we have found out. Z in is equal to 2.8 minus J 0.42. This much calculation you have to do yourself. Then the next point is look at these two. There are two circles now. One circle, one arc. Circle is constant. Arc circle, R is equal to 2.8. So on the Smith chart, locate the circle for which R is equal to 2.8. So how do you find out R is equal to 2.8? Look at the horizontal line or on the center of the along the center, which divides the Smith chart into two equal parts. Look at that horizontal line. On that horizontal line, the values of R is written. So it starts from the left end at R is equal to 0, goes up to R is equal to infinity on the right end. So on that you can find out where is the R is equal to 2.8. So go to that point and look at that circle. So the red circle here we have located, it is R is equal to 2.8. Then we have to locate the arc. Arc corresponding to minus J 0.42. How do you find out where is 0.42? Look at the outer perimeter of the Smith chart. So if you look at the outer perimeter, there it will be written 0.42, 0.43, 0.45, 0.01. All those will be written. So find out the arc, this blue arc that you can see. This is corresponding to 0.42. So at the end of the blue arc, if you look at the number is 0.42. So locate that number, which is 0.42. Then locate the arc that is passing through that number or which is touching that number 0.42. That is the blue arc. Now the point where the blue arc meets the red circle, that is the impedance point, normalized impedance point Z in. So that point is Z in, which is equal to 2.8 minus J 0.4. So we have located the point Z in, normalized impedance, input impedance point we have located on this lecture. This is one thing that we have done. Then we will find what we will do is, as I have told you, draw the constant VSWR circle. How to draw the constant VSWR circle? Look at the point 1 on the horizontal line. Look at the point where it is within 1. So put your rounder there, then take a radius up to Z in. So then draw the circle through Z in with the center at 1, which is the center of the Smith chart. So we have done the constant VSWR circle, which is passing through Z in is equal to 2.8 minus J and 0.4. So these are the simple things that you will do. Now you can do two things, either of these two. The first thing is look at the left point where the circle is crossing the horizontal line. Look at the crossing point of the circle, the constant VSWR circle, which is crossing the horizontal line. So from that point, draw a vertically downward line onto the scales which are below the Smith chart. So draw a line. So that line will cross these different scales, VSWR scale, gamma scale, those scales it will cross. Now where it crosses the VSWR scale, read that value, that will give you the VSWR value. Where it crosses the gamma scale, read that value, that will give you the gamma value. So VSWR and gamma you can find out this way. There is another way of finding the VSWR also. Look at the right. Look at the right hand side of the where it crosses the horizontal line. The point where it crosses the horizontal line on the right hand side, find out its value. That value is the VSWR value. So either way you can find out VSWR value. Similarly, you have to find out what is the distance between the center point 1 to this circle, or whatever is the radius of the circle. Take the radius of this constant VSWR circle, put that on the gamma line. So that radius length will give on the gamma line will give you the value of gamma. So these are the two ways in which you can find out gamma and VSWR. So we have dropped that line. You can see I have shown you here the expanded portion. In the expanded portion, you can see the vertical line that we dropped. That crosses the SWR line at the point 2.7. So therefore VSWR is equal to at 2.7. Then it crosses the reflection coefficient line, and for that it is 0.45. So gamma is equal to 0.45. So you can find out what is VSWR and what is gamma using this method. Then we have to find out what is the angle of gamma. Gamma, which is the reflection coefficient, it has two values. One is its absolute value or magnitude, other is its amplitude angle. So angle, to find out the angle, join the center of the circle on 2Z in and extend that line to meet the outer circle. Meet the outer circle of the Smith chart. So wherever it meets, find out, read the value. What is the value at the outer circle? The outer circle is at a distance of 0.24 lambda. So then find out what is the angle. Angle is given here. If you move in this direction, the counterclockwise direction, because we are moving towards the load, not towards the source. Now we are not moving towards the generator, we are moving towards the load. From the generator towards the load, we have to find out what is ZL. We are moving from the generator towards the load. So from the generator for the generator, we have found out what is the position, what is the length. That we have found out 0.24 lambda is for the generator. because we have extended the line from the center 10 point to the ZL and the Z answer to Zin. Zin we have extended, that means at the point 0.24 lambda. So this point, to note that it is 0.24 lambda at the for the input point. Then we go to move in the counterclockwise direction. As we are moving towards load, we will move in the counterclockwise direction by an amount of 0.1 lambda. So from that point, we move by an amount of 0.1 lambda, and then we draw a line from that point. Wherever we meet 0.1 lambda, from that point we draw a line. Next. So this is, we have moved a distance of 0.1 lambda. From that point we have drawn a line to the center of the Smith chart. That line will cross the constant VSWR circle at the point ZL. As you remember, along the line, along the transmission line, the VSWR remains constant. So VSWR at Zin is same as VSWR at ZL. Therefore, ZL and Zin both will have same VSWR. So you require a constant VSWR circle. So we have moved from the Zn point a distance of 0.1 lambda towards the load, and from that point, if we join the center of the circle, center of the Smith chart, that will cross the VSWR circle at the ZL point. So to find out what is the ZL value, wherever it crosses, there we find out what are the value of ZL. So there ZL is equal to 1 minus J1. So we have found out what is ZL, which is the normalized ZL. Once we know what is the normalized ZL, we can find out ZL by multiplying that with 50 ohm. So it will be 50 minus, 1 plus J1. So it will be 50 plus J50 ohm at the ZL. So load impedance will be 50 plus J50. Next. And then we have to find out what is the admittance. To find out admittance YL, what we have to do is invert ZL, 1 by ZL. As you know how to invert that, we know on the transmission line, if we move a distance of lambda g by 4, then the impedance is inverted. So if we move half a circle on the VSWR circle, half a circle from ZL, then we will reach a point which is YL. It will be inverted. YL is equal to 1 by ZL. Invert means it becomes 1 by ZL. So YL, we move a distance of or half a circle along the VSWR circle from ZL. We reach YL, which is equal to 0.52 minus J 0.52. Then multiply that with 50. So that will give you 27. 26. So it will give you 26 minus J26. So we have found out what is VSWR, what is gamma, what is ZL, what is YL, then V mix, V max points. So those two we will find out next. So these two we have found out. ZL, YL, we have found out ZL is equal to 50 plus J50. YL is equal to 2.6 minus J2.6. These two we have found out. Now what we have to do is find out what is V minimum and V maximum. What are the points for V minimum and what are the points for V maximum. So that we will do by looking at the VSWR circle. The left side on which the VSWR circle crosses the horizontal line, that gives you the V minimum point. The right side where it crosses the horizontal line, that gives us the V maximum point. So how to find out what is the V minimum, what is the V maximum? It is simple. from the load and look at the load point we have found out already. So from the load point, move in the clockwise direction towards generator and reach the horizontal line first. So wherever you reach the horizontal line first, so that distance gives you the V maximum point in this case. Then you again continue moving. So this is shown by the blue arc, outer blue arc with a red arrow. That you look at that. So that you continue moving till you reach the horizontal line set again. So that is the V minimum point. So that you can find out what is the V minimum point, what is the V maximum point in terms of wavelength by looking at the outer circle where wavelength is given. So this is what we have to do to find out VSWR, gamma, ZL, YL, Vmin and Vmax points. So Vmin, Vmax, we will calculate them from ZL. So from ZL, we will find out what is Vmin. Vmin is at a distance of 0.058 lambda, and this one is at a distance of 0.0338 lambda. The Vmin point. Okay, any input impedance we have found out. This is another example. In this example, input impedance is given. Input impedance Zin is equal to 40 plus J60 ohm. Z0 is equal to 100 ohm. You are required to find out what is the VSWR and what is gamma. This is the question. Question is input impedance is given and Z0 is given. Find out VSWR and gamma. So Zin is given, Z0 is given. Find out what is normalized input impedance. So Zin, small Zin is equal to capital Zin by Z0. That will be 0.4 plus J 0.6. Then you can calculate the gamma. Gamma is equal to, as you know, Zin minus Z0 by Zin plus Z0. That way you can calculate gamma. Gamma will be equal. That way it will be gamma will be 0.56. Angle will be 112. VSWR you can find out 1 plus absolute gamma by 1 minus absolute gamma. That will give you 3.56 or 5, somewhere there. Okay. Now we can do this using a Smith chart also. So to do this using a Smith chart, what we will do is first we will draw the Zin point, then we will draw the constant VSWR circle. Then on the constant VSWR circle, we will locate the point which is 112 because the angle is 112. So locate the point on the constant VSWR circle or the angle 112. So constant VSWR, as you know, it is 0.56. Gamma is equal to 0.56. VSWR is equal to 3.55. So draw the constant VSWR circle. Then draw an angle. Draw an angle. Angle will be with respect to the horizontal axis. Moving from the rightmost side, you take the angle. So that will be 112 degree angle. So that will give us the input impedance point. And then this is another example. The question is input impedance is given. Zin is equal to 75 plus 150 ohm. Z0 is equal to 75 ohm. Find VSWR, find the gamma, these two. So to do this, first find out what is ZL. ZL is equal to Zin is equal to, this is input impedance. So normalized Zin is equal to capital Zin by Z0. So then that will be 1 plus J2. Locate this point 1 plus J2 on this Smith chart. So that is ZL. So first we have located the point ZL is equal to 1 plus J2. First locate this point, then so we have gone 2 steps. Then third step is draw a circle with center at the center of the chart and radius from the center of the chart to the ZL location. So draw a circle. This is called the constant VSWR circle. This circle is called the constant VSWR circle. Then on the horizontal axis, draw a vertical line to the bottom of the chart from the center and the end point. So that you do. So that gives you the center of the end point. Then the next step is on the bottom of the chart, read what is VSWR value and note it. Similarly, read what is gamma value and note it. That I have shown you here. So this you can do. Next, once that is over, then draw a line which is passing through the center of the chart and ZL, which is meeting the outer circle of the chart. So draw a line. This is the red line that we have drawn. So draw this line. Then read the angle made by this line with the horizontal line and the value of gamma on the horizontal line. So these two things you read. So value of gamma gives you the magnitude, angle gives you the angle of the gamma. So that will be, so gamma will be 0.71 and angle for the gamma will be 45 or somewhere around 45 degrees. So this gives you everything about this ZL. ZL you have found out, VSWR we have found out, gamma we have found out, Zin we can easily find out by moving on the line. Then we will see another example. These are complete Smith chart tool. We used complete Smith chart. Then I will show you this partial Smith chart as we started with in the beginning with the partial Smith chart. Here the question is simple. Use a short-circuited section of air field and TEM. TEM is transverse electromagnetic mode. TEM 50 ohm transmission line. This means that we are using a transmission line whose characteristic impedance is 50 ohm. Okay. Find out what is our beta. Beta is equal to K0, that you know, which is equal to 2 pi by lambda. Then lambda G, which is lambda D. Lambda D is within the dielectric. D stands for dielectric, G stands for kite. So lambda G, which is equal to lambda G, since it is in free space, air field, so it is in free space. Therefore, lambda G is equal to lambda G is equal to lambda 0. Beta is equal to K0 is equal to 2 pi by lambda 0. So, of this, to create an impedance of Zin is equal to minus 25 minus J25 ohm at frequency 10 gigahertz. Now, you know from the transmission line theory that if we use either a short-circuited transmission line or an open-circuited transmission line, that line will act like an admittance, okay? Pure admittance, that can act as a pure admittance. So, in this case, what we will do is we use a short-circuited transmission. So, here it is given, I use a short-circuited section, so we will use a short-circuited section. So, we have look at this figure for the transmission line. We have a short-circuited section. At the load, we have a short circuit. Characteristic impedance is 50 ohm. Beta is equal to K0. Then input impedance. Find out what is the input impedance. If characteristic impedance is 50 ohm, input impedance is given. That we require. We have to find out what is the length of the short circuit. input impedance is given to be 25 lambda minus J 25 lambda. So Zin is given, so then you normalize it. So Zin N, which is the normalized Zin, is equal to minus J 25 by 50, that is minus J 0.5. So that we have found out what is Zin normalized, that we have found out. Then we have to find out what is L. And length we can easily find out by using this formula. First, locate what is Zin, normalized Zin, and locate what is short circuited point. So first locate the short circuited point, that is the red dot written SC 0 lambda G, that is the short circuit point. Then from there we have to move and find out where Zin is equal to minus J 0.5. So on the line, first locate where it is you have J 0.2 or 0.5 or minus J 0.5 ohm. So locate minus J 0.5 ohm. So look, that is the second red dot on the lower half. So the red dot on the lower half is the second red dot. Now we are moving from the short circuit point towards the generator. So we have to find out what is the length by moving in the clockwise direction. So you can see the arrows are rotated, arrows are given in the clockwise direction. So start from 0G, 0 lambda G, move in the clockwise direction till you reach the 0.5 lambda G point, or which is approximately 0.426, that is 0.5, very close to 0.5, or 1 minus 1 by 2 lambda. Then find out what is the length of that section. So that length L is equal to 0.426 lambda G, that is the value given for that, minus 0. Lambda G, which is equal to 0.426 lambda G. Why minus 0. Lambda G? Well, the reason is we have not crossed the 0 lambda G or 0.5 lambda G, we have not crossed. Had we crossed the 0.5 lambda G, then we would have made minus 0.5. So this is A is equal to 0.426 lambda G. Now lambda G is equal to lambda 0. Lambda 0 is equal to C by F, which is equal to 2 pi by K0. Lambda 0, you know, is frequency is giving 10 gigahertz. So lambda 0 is equal to 3 centimeter. If lambda 0 is equal to 3 centimeter, and then L will be 0.426 into 3 centimeter. So that from that you will get it to be L is equal to 1.28 centimeter. So the length of the transmission line section to give us an impedance of minus J 25 ohm is 1.28 centimeter. It is the same problem with an open circuit. So use an open circuited section of 75 ohms. Y0 is equal to 1 by 75 ohms. Air field transmission line at F is equal to 10 gigahertz to create an admittance of Yin is equal to J 1 by 75 S. So here follow the same principle as in the previous case. You will get L is equal to 0.375 centimeter. So following the same principle, we will get this. So do this yourself. This is a homework. I am not drawing this. You do this at yourself. First normalize it, then find, locate what is the value for Y is equal to J 1 by 75 S. On that you locate. Then find or rotate in the clockwise direction and find out the N. I will rotate in the clockwise direction from open circuit point and find out the N. So we'll take a break here for 5 minutes. Then we'll come to matching, impedance matching, using transmission line and without using transmission line. We'll come to impedance matching. Today we'll discuss the basics of impedance matching. Next class maybe we'll see the impedance matching and so on.